to give you. But I don't think the quiz is going to be that bad. Today, what we're going to talk about a little bit is how to punch things in your calculator. So if you don't have a calculator, you might want to find one for the quiz.
Is that the quiz?
Huh?
Is that the quiz?
There's a question on the quiz that it's basically all it's asking. A lot of students see these problems and they haven't. There's a lot to them. They, it's represented, something like this, and it's, sample originally having 1 gram of uranium 225, blah 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 blah. Here's the function. Now, in some math classes or maybe a chemistry class, you would have to come up with that formula by yourself. But we give you this formula because we're not assuming you have a chemistry background. So all that we do here is can you plug in these 3 numbers to this function? Now, some students have problems plugging in this function because order of operations on your calculator. So if you have 1 divided by 2 exponent t divided by 1620, every calculator is going to handle that differently. So we have to be a little bit careful. And then the last thing we're going to talk about is when we have an e, something like this. And again, in the denominator. So there's going to be multiple things we have to think about the way we plug it in our calculator. Some of your guys' calculators will have pretty print, so you can see how exactly it's going to show up. Maybe that calculator does. Your calculator probably end up having pretty print, so you can see what's in the numerator and what's in the denominator. But most calculators, you just give you a line. So you have to be really careful where you put your parentheses at. And that's all really is. Can you plug in 0 and can you plug in 8 into this problem? And what does it represent? So yeah, there is kind of a question on your quiz. Can you plug in the right series of buttons in your calculator? So I gave you guys back quiz 5. Anyone come in not get their quiz back? Turn it in. We have, I gave you yours on your table. Okay. Most of you guys did pretty good on the quiz. I'm going to take a few minutes to go over it. Does anyone have any questions on number 1? Come up with the inverse function of x equals minus 9x plus 4. I've also posted the answer key to Blackboard. If you go into notes and handout and lectures for chapter 4, the answer key is posted right here. So you can find that. Any questions on A? Very similar to one we did in class. B, we kind of went over it a little bit. A couple people got down to x cubed minus 8. What was the answer? X cubed minus 8 equals f inverse of x. There was a couple people that had y cubed minus 8. They forgot to switch the role of x and y.
I factored out the x cubed minus 8.
Oh, okay. And you had
X minus 2.
the difference of cubes.
2x plus 4, yeah.
Oh, totally missed that. Yeah, let me see what's going on there. Yeah. Yeah, I just saw that and was like, I have no clue what you're doing, but I see that now. And you don't have to factor it. You can just leave it here. I'll give you your points back there and upload that to Alex. This is a perfect cube or difference of cubes. It can be written as x cubed minus 2 cubed, which could be x minus 2, x squared, always positive, oops, 4. So same, opposite, always positive. So yeah. So another thing that I kind of was a little I try to emphasize that you need to write f inverse of x, or in this case, it would be k inverse of x instead of y equals. Because y doesn't equal that, the inverse function equals that. If you put f inverse of x, that was fine. But I wanted to see the inverse, that you understood that was the last step there. Very similar here. I had a couple students. The answer was the cube root of x plus 5 over 2 is in inverse. I had a couple students just write the cube root of x plus 5 over 2. Be a little careful, it's the cube root of all of it. And D was very similar to one we did in the lecture. Turned out f inverse of x is minus 2x minus 4 over x minus 1. A lot of negatives going on there, but not anything too bad. So I'll change that in Alex after class. Okay, does anyone need an extra copy of 4.2 where we left off? What? I just want to take a minute to go over Alex problems. So there's a little disconnect between Alex problems and written problems. This one's not too bad. We're just taking the point, we're shifting it whatever way we need to go, right? It already gives you kind of the sketch. See if I can go to, I think it was number 4. Number 3? Number 3, we're going to talk about how to go about sketching this one. And some students had no problem sketching it on Alex, but they couldn't sketch it in the real world. And there's really no, if you can do it on Alex, you can do it on paper. So Alex here, there's a couple different ways you can do it. You know, how do you graph this? First, they ask you to find the asymptote. So if we find it, here we have a horizontal asymptote, it would be shifted down 2 units. So I could have a horizontal asymptote there. That's just giving Alex kind of some parameters to outline. You're going to do the exact same thing when you go to, if you were going to physically graph this, you would say, okay, I'm not going to be able to pass this dotted line because that's my horizontal asymptote. Then I need to find a point, and I can find 1 point and then know just kind of the overall shape. Here they want you to find at least 2 points. There's 2 ways you can do it. You can just get a pencil and put a point. Here, if I have x equals 3, then I have a half plus a, or half minus 2, which is kind of hard to see on the graph. So you can actually click this little point here, and it's allowing you to put in any point. So you could say x is minus 3. So when x is minus, or not minus 3, sorry. When x is 3, what is y going to be? You can actually use the e value because it's going to be impossible not to estimate that. So if I plug in 3, then I have e to the 0, which is 1. So that gives me a third. And I can plug in a third minus 2. And then I can plot that point, and it's going to plot that point right there on that graph. Yeah, so that might save you guys a little bit of time there. And you need 2 points to be able to graph this function. So I can put in any other point. I could put in x equals 4. So when x is 4, I get a third e, right? E to the first power. 4 minus 3 is 1. Minus 2. And then plot the point, it's going to give me the point there. Then once you have 2 points, you can click the graph, and it's just going to kind of trace it. That's all you're doing kind of by hand as well. You know, this point to this point, you know it's going to be an exponential growth function.
How do you get the third? I don't. How did you
get the second point?
No, how did you get the 1/3? You have a half and then.
Did I plug in a third? I should have plugged in a half if I did. Let's erase it and plug in. I plug in x's 4, then this should be a half in this problem. A half e to the first power minus 2. So yeah, if I would have done that, plotted the point and got that. So a little bit different. But yeah, you have to be a little careful. I probably saw the 3 instead of third. Should have been a half. No, that's a good catch. Does anyone else, you guys see that? Now, students can do this all day on Alex, but then when they get a piece of paper and it's blank, they're like, I don't know what to do. You do the exact same setup. Just horizontal asymptote. What can I not pass? Now I need to plot a point or maybe 2 points. Really, you only need 1. Then to know that you're going to have an increasing or a decreasing function. If it was if the e instead of the e, if it was a half, the half was in parentheses, it would look the very same, except it would be in a decreasing function. Still go through that same point. Does that make sense for graphing it by hand versus an Alex? Last time we talked about this function, and that's kind of what the Alex representation was. You're able to plot points in Alex, do the same thing, plug that e in your calculator and get an approximation. Here it's kind of difficult to see what a third, in this case it was a third, maybe that's where I got a third plus 3 would be. 3 plus a third, where does that, show up on the graph? But it's either going to be an increasing function or a decreasing function, increasing rate of growth or a growth function or a decay function. And you really only need 1 point for that. Alex thinks you have 2. But another important thing is the horizontal asymptote, because it's going to ask you the domain and range. Domain is all real numbers. For any exponential function, the domain's all real numbers. The range then has to do with the horizontal asymptote. How was it moved? Right here would be minus 2 to infinity. So we have this exponential function, and it's used to various branches of math, one in financial mathematics, another one in biology. We're going to look at the 2 applications here. These formulas will be given to you, so you don't have to memorize them, but it's a way to calculate how much interest, depending on if you're borrowing money or if you're investing money. So if you're investing money, it's how much interest you get. If you're borrowing money, it's how much interest you have to pay. But the formulas are the same, and it comes from how many times it's compounded. So this is simple interest. If you borrow money at simple interest, the amount of interest you pay will be the same if you borrow it for a day or if you borrow it for a year, right? In a sense, I mean, the time is in there. Simple interest there. It's the principal times your interest rate times your time. A lot of times in years. So if you borrow it for 6 months, the time would actually be 1/2 because it's measured in years. And we'll do some examples of this. This formula is with compound interest. So if I borrow it for a year, if it's being compounded daily, I'm going to owe more money than if it's being compounded quarterly. So N is the number of compounding periods, right? So I have my principal, I have my interest rate, I have the number of compounding periods and the years I borrow it from. Simple interest, it's only calculated once. Compound interest, if you don't make a payment or if it gets compounded quarterly, and then gets compounded 4 times in that year, so your interest kind of grows. And then there's a thing called continuous compounding, and for continuous compounding, we use E as our base. So if we take the limit of this, it goes to N goes to infinity, we get E. So here's the application. Suppose you borrowed $5,000 or you invested $5,000 and it pays 6.5% interest per year, so T is in years, under the following options, compounded annually. How much money are you going to have at the end of the year if it's being compounded annually? That's simple interest, right? So use the formula I is PRT. So we have 5,000 times our interest rate, 0.065. A lot of times your interest rate will be given in percent, so you have to convert that to a decimal to plug it in your calculator. Compounded annually. So if you get your calculator out, a 0.065 and then times 1. If I find my calculator, or if I find my answer key. Let's go to what do we get? We'll just go to my calculator then. 5,000 times 0.065 times 1. $325. So I've made $325, $25 on this investment. If it's compounded quarterly, means it's compounded 4 times a year. So the interest here is the principal plus 1 plus 0.065 divided by 4 times 4 to the 1. So following this formula, N is the number of times I'm being compounded, T is the number of years I invested, R is my interest rate, and P is my principal. So like I said, I'll give you these formulas, and then it's up to you to know how to plug them in. Question?
For the formula for the B1 that's in parentheses,
Yeah.
what is its function there?
Here, this is the number of years. This is per year.
I meant on B. I'm sorry, I wasn't looking at you.
B, this one?
Yes, that one.
Because it's kind of like this one. It's principal plus, so this is actually, yeah, this is the amount, the future amount. So here we'd have to add 5,000 in here to get the future amount because it's worth $5,325 at the end of the year. Here, it is the future amount. You don't have to add it in. It's already added in. If you were to kind of distribute this, even though it's illegal because we have that NT there, we're thinking of we're still going to have the principal invested at the end of the year plus our interest.
So the one is standing for the principal.
It's standing in there for the principal. Yes. Yeah. Here, we want to know how much we're going to have, how much money we're going to have at the end of the year. So at the end of the year here, we're going to have $5,325. We made $325 on interest. For B, we don't have to add in the 5,000 because that one is that placeholder for that. So let's look at how to plug this in our calculator. My calculator, it's going to be a little bit different setup. Yours might be a little easier to deal with. But if I plug in 5,000, open parenthesis, 1 plus 5,000, I have to actually hit the parenthesis here. 1 plus 0.065 divided by 4. Raise that to the power. So a lot of times you have a caret. Raise that to the 4th power, and then hit enter. It's actually only calculated before the 5,000. So then I need to multiply that by 5,000. Oops. Take this times this number times the 5,000 out in front. And that gives me $5,333. Yeah, 0.00, huh?
One syntax error.
Syntax error, so let me see.
It uses parentheses.
This is what you entered, okay? So here's your problem right here. It should be this one. You should close it for. So you have 5,000. That's good. Open parentheses. 1 plus this divided by 4. Close parentheses. Raised to the 4th power.
It's like miniature popcorn. It's like toasted cream.
So yeah, you might want to try to enter it again. Yeah, you want to be very careful with your order of parentheses. There's my answer key.
Yep, and that's
You
really odd.
Yeah, those are not the right numbers. I don't know where those. I think it's because I had 5,000 maybe, or I put 9,000 instead of 5,000. They didn't use this anyways. Yeah, I don't know where those numbers came from. Different problem. Okay.
The exponent there, then.
This one?
Yeah, when you raise it to the periods per year. not
Yeah.
the number of years.
Yeah.
Why is that there? I mean, I understand that's a function, but why
Be-
raise it to the power up?
Because it's being it's being compounded that many times throughout the year. So you take your interest rate and divide it by 4. That's the interest rate per compounding period. And then if you multiply that by each other 4 times the 5,000, that's going to give you your amount for 1 year. And all this is for 1 year. But I said, how much would I have at the end of 5 years? I'd pretty much do the same thing, except this would be So we got $5,333. If it was compounded monthly, this is not I, this is A, which is going to be the amount in the account after 1 year, it's going to be my principal times the same setup. It said 4, I have 12.
That's kind of same way I did.
Yeah. So what you do is you take the interest period for the year, divide that by 12. That's how much you're getting per month. But you're getting that every month on top of each other. It's being compounded. So really your interest is earning you interest, which is the fastest way to make money. If it's being compounded, continuously it's getting compounded is the way to make the most money. If I compound it annually, I only make $325. If I compound it quarterly, I make $333. Here in your calculator, some of your calculators, if you input it once correctly, you can actually go back to your command line, change all the 4s to 12s. You have to be really careful that you insert it and don't just change 4 to 12 because it's going to shift it over. And that's going to give you the correct answer. So if I can plug this in, 1 plus 0.065 divided by 12. Raise that to the 12th power. Did I swear it? The 12th power, multiply that by 5,000. And we made an extra $1.86 by compounding monthly instead of quarterly. Yeah.
Dailies more than much more.
Yeah, I mean, it's somewhat limited.
Like a double.
Yeah. 86, we'll say. Daily is going to be 365, so it's principal plus 1065 over 365 to the 365.
Yeah.
So 1 plus 0.065 divided by 365 raised to the 365 times 5,000. So $5,335.76. Are you guys getting the same thing I'm getting? You should be. And then that was for D. E is going to be compounding continuously. So you're going to take PE to the RT. Yeah. So you take 5,000 E to the 0.065 times 1 because it's for 1 year. I don't have an E button on this calculator. If I go to web scientific calculator, it will have an E button. And I can type in 5,000 E to the power 0.065. And I should get $5,335.70, or we'll say 80 cents. So this would be $5,535.80. So compounding daily, I get a couple, 5 extra cents, 4 extra cents. Oh, that's why those numbers are different. So here, we determine the total amount in the count after 10 years. So now with 10 years, we change all the T's that were 1s, we change those to 10, and you'll get the numbers that were on the answer key.
T's that were 1.
So here, this 1 was just for 1 year. I was just looking at 1 year. But if I wanted to look at 10 years, I would have the interest would be PRT. So that's going to be it's going to be 5,000.065 times 10. Which would be 3,250. If I add that to 5,000, I see I get 8,150. Is that the number I got when I
think you put in 0.63 instead of
Oh,
0.65.
thanks. 0.63, yeah, instead of 0.65. 5,000 times 0.65 times 10. 300 and yeah. So that gives me, oops. .065 times 10 plus 5,000. 8,250, yeah. 8,250. So you can compare the difference between 1 year investing and 10 years investing. You guys see that? T, if I wanted it in 50 years, how much money I would have, eventually we're going to be able to solve how many years do I have to invest it to have $10,000. Those are going to have to use logs. And so when we learn logarithms, we're going to be able to solve those problems. Right now, we can just say, given the years, find how much money I'm going to have.
So I just want to make sure I understand the A, like if we did the 10 years, the P times 1 plus 65 would be P times 10 plus 65.
It would be P times 0.065 times 10.
P times 0.0.
This is P, this is your R, and this is your T.
No, I mean not that one on B.
Okay,
On
yeah, B, it's going to be 5,000 times 1 times 0.065 over 4 times 10.
Okay.
Because 4 is still a part of that. It's being compounded 4 times a year.
So the 1 still represents the.
Yeah, the 1 just
The
represents
original.
how, yeah, the time, the T. And I was assuming T is 1 for all of them, but it actually T should have been 10.
Okay. So that'd be 4.
Yeah.
Okay.
So for C, I would change the 4s to 12s. Right? And I would calculate that. The exact same setup, all the 4s then becomes 12. For D, I would change all the 12s to 365. And then for E, I would have 5,000 E to the 0.065 to the 10th.
Do you have to do all those different ones, or can you just do like the top one?
For this problem, it's asking how much money are you going to have at the end of the count for A, B, C, D, and E. But if I ask you how much money you're going to have if you're compounding continuously at the end of 10 years, you would just do this one here. So, I mean, the problem is just showing you all the different options that they can give you.
Okay.
Does that make sense for those formulas? Okay, I'll give you the formulas, but you need to know which one to use when. And then key to also think, if you add P, you get A here. You have to add P to the simple interest because the simple interest is only going to give you the amount of interest. But compound interest and continuous interest is going to give you the principal plus the interest built in.
Because of that one, right?
What?
Because of that one.
Because of that one, because it's taken the principal plus how much interest I made for each compounding period.
Yeah, I understand.
So, applications, let's look at this one. If I have 220, if I have 1 gram of radium-226, and I want to know how much is present after T years. So a lot of times T is going to be measured in years. Sometimes it can be measured in other things. So you have to be a little careful if it says, you know, T is measured in minutes. How much are you going to have after 30 minutes? You just plug 30 in. It says T is measured in hours. How much will you have after 30 minutes? Then you would actually plug 0.5 in. It doesn't really come up much, but it's important to know what it's being measured in. Here I want to know how much of this substance I'm going to have after these years. So I plug in A 1620. So I have 1/2 to the 1620 divided by 1620.
Now with the 1620,
Mm-hmm.
you have that, would you put that in parentheses divided by 1620?
In your calculator?
Yes.
More than likely, yes. You would have to have open parentheses, 1/2, close parentheses, caret,
Right.
open parentheses. Here I know it's 1 though,
Okay. See, I got 0.5.
which is the answer,
Oh.
which is 1/2. Right, 1/2 to the 1 power is 1/2. Here, if I plug in 3,240, I have 1/2 to the 3,240 divided by 1620, which is 1/2 squared. What's 1/2 squared? A fourth, which is 0.25. What this formula is saying is half of the uranium disappears every 1620 years. It's the half-life.
Disappears every 30 to 40.
It's half of what's left. So half-life means if I have 1 gram,
Right.
half of that disappears in 1620 years.
So
Then half of that disappears in another 1620 years. And
a
then
quarter of a half.
Yes.
At 32.40.
Yes. Yes. So at 4,860 years, I'm going to have a half to the 3rd power, which is an 1/8, which is 0.125. So that's how they a lot of times do carbon dating and stuff, that they can take, the half-life, so they know, how much carbon is left in the fossil after so many years, and that's how they can backdate things. But the application here, sometimes students will read these problems and be like, I don't even know what to do. Just look at the formula, and then you plug the number in the formula. Be a little careful on your calculator. The next one we're going to look at, these are just some examples from Alex. We have one here, which is actually going to be on your quiz, so I'm going to wait on that one. I'll go over the fish one. So this formula tells you the population of fish at any given point in time. If it wants to know the initial population size, what do I plug in the formula? When time is 0. Anytime it says initial amount, that means we haven't started the formula. So we plug in t equals 0. At t equals 0, we have 1,000 divided by 1 plus 7 to the e to the 0. It should be on the very last one, because the other one's just kind of from Alex. Is it not on the very bottom of the last page? What is e to the 0?
1, right? So it'd be the 2.
1, right? B to the 0 by definition is 1. Anything to the 0 power is 1. So yeah, here I'd have 1,000 divided by 8, right? Because this is 1. 1 plus 7 times 1 would be 8. So what's 1,000 divided by 8? 125. So there's 125 fish to start. What is the population after 8 years? 1,000 divided by 1 plus 7 e to the minus 0.3 times 8. Really, it's testing. Can you plug in your calculator? I mean, these problems look scary, but really it's saying, can you plug 8 into where t is and evaluate your answer? So be careful with order of operations. Plugging it in, you probably want to open parentheses 1,000, close parentheses, divide, open parentheses, 1 plus 7 e caret, open parentheses, minus 0.3 times 8, close parentheses, close parentheses, close parentheses. So going to this scientific calculator, it will give me a pretty print up top. So if I hit 1,000 divided by, open parentheses, 1 plus 7 e to the minus 0.3 times 8, close parentheses, close parentheses. So you see on top, it gives me kind of the setup. Some calculators will actually do that for you. So we get 611.6, and your Alex is going to ask you to round to the nearest fish. So if the next decimal is above 5 or above, you round up. If it's less than 5, you round down. So it will say round your answer to the nearest whole number if necessary. So here we have 612 fish. So the population is increasing. So you guys see that? I'm going to go ahead and give you guys the quiz. I think there'll be enough time to get it done in class.
Today.
Yes. It's pretty basic. So look at, there's one graphing, and then on the back it's going to plug in your calculator. And I'm going to kind of walk around. The domain and range for an exponential function.
The domain. Is that gonna be?
Yeah, the first three are pretty straightforward.
There's a symbol. All real numbers.
Yeah, you could put all real numbers.
Then I can write it out.
Typically, Alex will only accept interval notation, but you could put all real numbers.
That's.
You say x is an element of all real numbers. X is a set of x such that x is an element of all real numbers. Various different ways to write it. Typically, interval notation in college algebra is hit on the head a lot.
So the range,
So what would the range be?
wouldn't it just be, zeros and things? Okay.
Team effort.
Okay.
No, I just want to have something to, because the more I can give you as written homework quizzes, the more I can put in Alex, the more I can drop lower ones. I'll help your Alex grade. Because if you miss one and I only give you two, you have 50% Alex grade. If you get 100 on the other one. So. I didn't cheat one around.